what was done 2 years ago, but it's essentially the same story. So yesterday we worked with only one grid. So we had this grid for the Iroise Sea with it was actually a grid with triangles, but it works exactly the same with a regular grid with squares. And today we'll talk a bit how we run not just one grid but several grids together. And the idea of using this multi-grids is that you can save some time by having different time steps in different regions and stuff like that. So I'll talk. Yeah, this W3 multi will replace the W3 shell that we used yesterday, and there will be a few slides about how this works in practice in terms of the numerics. I think I talked about it a little bit yesterday already. So the this feature with multi-grid was actually already in version 3.14, so that was 2002, 2003. And the idea is that you can have two grids which are two-way nested. So the small grid is average to get the data on the coarse grid, and the coarse grid interpolates on a fine grid. So it's a two-way communication. And one of the issues, and it was the same issue with the nesting, is you have to make the two grids consistent, especially in how to define the boundary conditions. And so this is why we will be using this afternoon this grid generation tool from NCEP, which is a MATLAB-based tool. Yeah. So when you run with different grids, it is exactly as yesterday. The only difference is that we replace W3 shell by W3 multi. This means that each grid will have its own moddef file, the model definition file. This guy, moddef.w3. If you have a grid called GRD1, now it's going to be called moddef.grd1. And you'll see how that works. Okay, so basically for one grid, we did that. We had the symmetry. So we maybe went a bit too fast yesterday. You didn't quite pay attention too much, but in the grid.inp, there's a line where you tell it what is the depth of the node. So either it was defined in the file itself, there was this big number times 1, so the depth was the same everywhere, or we were reading the depth data from the file. And actually, yeah, the funny thing about the triangle is that the depth is together with the structure of the file. That was maybe a bit hidden, but basically you have a symmetry file. You can have for structure grids an obstruction file. So this obstruction is the information for masking part of the energy flux. So if you have small islands which are not resolved in your grid, you have this obstruction file that tells how much energy flux will be removed, and this obstruction is two-dimensional. It's done in two different directions. We have one obstruction for the X or east-west component, and one obstruction for the north-south component. Then there was this mask mod, the mapstat or file, the mapstat.w3, which defines the points that are inland or on the ocean or can be dry or something like that. And then all the model settings that were essentially defined in the grid.inp, and all this stuff is combined by W3 grid, and it generates a moddef.w3 file. So this is for one grid. Now, what you do if you have several grids, you do it just for one grid, and you rename. So you move this file into moddef.grid1, and then you do all that stuff again for second grid, and you rename the result moddef.grd2. And so forth. So W3GRD will always create this file, and then it is up to you to change the name of this file to have it as what you want. So you do that with your several grids. So imagine you have a global grid, Bay of Biscay grid, and something of Portugal here, for example. Then there are possible also other grids, and these other grids are, so you will have to define now grids for the inputs, especially if you want to use the same input for all your grids. Let's say you want to use ECMWF, Global Winds, or NCEP. DFS win for all your 3 grids. So you have to define a grid for the forcing. Of course, the wave parameters will not be used. It's just to define the place where you have the nodes for the winds. But you still do the same way. So you tell it, okay, my grid it looks like this. So I have so many points in X and so many points in Y, or latitude and longitude, and then it creates a moddef file. And this moddef file that will be renamed by you as moddef.dfs if you want for the input, the forcing. This moddef file will be used then to do the interpolation during the computation time. So the model, the W3 multi, will automatically interpolate your forcing field on the 3 different grids. And because maybe you're going to have different spectral resolution in your different wave models, so say you have 24 directions in the global model, you have 36 in the coastal model, and not the same number of frequencies. If you want to have the point output for the spectra on one of these 3 grids, or even interpolate on a different spectral grid, you also have to define grid.inp for the spectra output, and that will be this one. Okay. So there's moddef files for the grids, for the forcing, and for the spectra, and that's to have a consistent spectral resolution on the outputs. All right, so this is what happens if you do GRIB output. Say you have the binary result of your W3 of your single grid. You process it to get the GRIB file. Now what's happening is that we're still use the same W3 GRIB or the same W3 ULF or OutF, but the result of the model run is not called like this anymore. It's called like that. So the first grid, when W3 multi runs, it will generate a file which contains this out.drd dot and the name of your grid. And so again, it is up to you to link or rename or whatever you want to do. Usually I do a link because well, you have to be careful with links because sometimes you can erase your files. But so you link to this file, then you do the post-processing, and then you get the results. Okay, and if you want to do that for the 3 grids, you have then to remove this, link the other grid, do the post-processing, and get the result again. Right. So that's the idea. Is that there's only one program that changed to W3 shell, which is turned into W3 multi. All the other programs we used yesterday are the same programs. And so, because they are the same programs, they use the same file names in input, which is always this, for example, for this one. And so, of course, if you do all that by hand, if you have 10 grids, it's a lot of work. So, of course, we have some scripts to automate that, to do the moves and all that stuff. All right. So, W3 multi. Yes, this is what I said before, actually. Uses 3 types of grids. So there's the actual grids for the model itself, what we used yesterday. So the moddef.grd1, for example. And that could be a triangle mesh, it can be a curvilinear grid, it can be a square grid. Then there's a subgrid for the input, and that's really useful when you have the same input for different grids. You can also have different inputs for different grids. So instead of having just one wind grid, you can have several wind grids. They have a DFS grid and a WRF grid and a second WRF grid. And then you have to tell the W3 multi which grid will use which forcing. But for each forcing, you have to define a grid. And so we do that typically for we have a grid for the winds, a grid for the ice, some grid for the current, and all that stuff. And again, for wind, you can have multiple wind grids. And there's a special grid for the point output, and that's useful to be able to post-process the spectra on the same spectral grid. In what we do actually in our routine operations for the Plasmia project, we have the same spectral resolution everywhere, so it's very simple. The point output spectral grid is the same as the other ones, but it could be different if you really wanted to do that. And yeah, so then how to run this W3 multi? So there's several ways, and one example here, I will show the data flow for that, and the model setup. So you have these 3 grids in which your model will be running, and they will be called GRD1, GRD2, and GRD3. Here we will use these grids driven by ice and wind from a same grid called input, okay, which defines the resolution of the wind and the ice. When you run this, each grid will have its own restart file, okay, and its own out GRD file. So the output of W3 shell that we had yesterday will look the same as the output of W3 multi, except that now they'll have slightly different names. And here we'll make an example with, in which all the point output, the spectra time series, are written to a single file. There's also an option to have spectra from each grid, but then if you have a point which is in 2 different grids with 2 different resolutions, you have to spectrum twice, once from the coarse, once from the fine. I never used this option, but it's another option. And there is, of course, all that is detailed in the manual. And if you're a bit lost and want to see some other examples, the folder with the reg tests contain all these MW3 cases that have several examples of different types of ways to run the multigrid. All right, so we have our 3 grids. We've done W3 grid 3 times. Each time we move the moddef.w3 to moddef.grd1, second time grd2, third time grd3. If we actually run the model before, or if you want to get the starting conditions, you can do W3 STRT 3 times, but then you have to move restart.w3 into the proper GRD, restart GRD1 and restart and so forth. We have the grid definition file for the input field. We of course have the wind and the ice, and the okay. And here the convention is that yesterday we had some files called wind.ww3. Now, because the grid is called input, the file that goes with it should be called wind.input. Of course, if you have a first grid input1 and a second grid input2, you will have a file wind input1 and a file wind input2. Okay. And yes, there was a special grid definition for the point output. All right, so we do have input file for the W3 multi. It is more or less the same principle as the input file for the shell. There's just a few more lines because you have to tell which grid is using what and what other grids are you using. Okay, and all that information will be used by the program called W3 multi. And this W3 multi will produce several files. So one is equivalent of the log file that we had before, except that it's a log for the entire multi thing, so it has some information about the communication between the grids and what's going on. So it's a slightly different format. The log files, the same we had yesterday, are actually, they still exist, but we have a log file for each grid that tells if it's reading or writing and things like that. In our case here, when we're doing the common point output for all the grids, if you look in the log file, you will not see the crosses in the point output. This is because the point output is done by the entire multi, not by each grid. Okay, so don't worry if you don't see the crosses in the P column, but you should get the crosses for each of the field outputs in the F column of the log file. Then the multi will also produce a restart, and the way it looks is that you get the first restart is restart 001.grd1 for the first grid, and so forth. And the binary output file for the grids will be one output file for each grid. And if you have requested the common point output, you have the output point outPNT for the point. And it's a point here because it's defined with the moddef point. If you call it moddef P, it's going to be outPNT P. All right. So what's important to tell WaveWatch and the W3 multi is how the different grids are connected to one another, and they have a hierarchy, and this hierarchy is defined by this rank. So yeah, lowest rank number is highest in the hierarchy, right? It's like the global grid. Usually the coarser one will be rank 0 or 1, I don't know. I think it starts with 1. Rank 1. Then below that, after that, the finer grid will be rank 2, and then so forth. You have different ranks. In practice, you can have grids of the same type, means rectangular, regular grids can be of the same rank and be overlapping, and WaveWatch will manage the overlapping. Say, for example, you have the Portugal, north of Spain, and then the Bay of Biscay. You can overlap the Portugal and the north of Spain and these three. The one feature which doesn't work is to have grids of different types, say triangles and squares, at the same rank. So if you want to do Portugal and north of Spain, one with triangles, the other one with squares, you have to make one rank 2 and the other one rank 3, so that there's no conflict. But that should work. I'm not using it very often, but I think there's a test case with that. And and of course, the grids with lower rank resolution, right. The coarser grid, lower resolution, gets a lower rank, and there's a two-way nesting between grids. All right. Then there's also a notion of group, and the benefit of this group thing is that grids can be running side by side on different processors, different CPUs of your cluster. And that can actually speed up a lot the computation. So for example, in our Prévimère system, we have one grid for the northwest Atlantic, a northeast Atlantic, another one for the northwest Atlantic. We have some stuff for the Caribbean. And all these three are in the same group, and they are running on different CPUs. And they are on the same rank. And so for each grid, in that mosaic of grids, you need to provide the following information. And of course, this is done when you run w3 grid.inp. So one is a mask for this grid, so the land-sea boundary. The location of the input points at which the grid expects to get data from the lower rank grids. So this is the same idea as if you do nesting. So you have to tell WaveWatch where the input is coming from the parent grid. And of course, you need to provide the time steps for each grid. So all this stuff is done when you run the w3 grid. Okay, so you do that for each grid. Then, when you have all these modDef files and you're going to run w3 multi, the information you have to provide inside of w3 multi.inp is this notion of grid rank and the group number. Which grid is using which forcing? Say my global grid is going to use the GFS winds, and my Portugal grid is going to use a local WRF, for example. Then you need to tell it the output you want from each grid or from all the grids together. You could actually have different field output for different grids. I never use this, so I always have all the same field like HS, TP, mean direction for all the grids. And something important for optimizing the CPU time, you can provide a load balancing information, and that's not done automatically. So you have to tell WaveWatch that the first grid is going to use 50% of the CPUs. The second grid is going to use 30% of the CPUs, and the last grid, maybe it's smaller, it's only using 20% of the CPUs. In that case, you'll have to be a bit careful to. Oh no, yeah, separate. So there's also CPUs that are dedicated for the output, and so this is defined also in the multi. So you tell it how you want to do the processing for the output. If it's done by only one node, or each node does the output, and that the efficiency of that will depend on your architecture. If you have a parallel file system or not. So the idea is that you try it and see if it's faster or not, and then you can adjust that. All right. So in practice, you could also be nesting a multi-grid system inside of some other information. So you could actually also provide a nest file for the entire multi-grid system. And yeah, there's some interesting features there that you could also do that for the higher rank grids, but the data has to come either from the file or from the mosaic. And you cannot mix file data, the nest file, together with stuff coming from a grid, because it's just too much different features. That's not supported. And there's an option, you can actually write a nest file when you run the W3 multi if you want to keep the nesting information for running the model standalone later on. All right, so much for all the features. And by default, yes, the nesting information, so what was before the nest file, by default it's not saved to the file because that would be a lot of disk space. All right. So Henrik was advising us here about these different things. When you build a grid, yeah, the idea is to start from the coarse resolution when you generate your grid system, and then you after that you generate high resolutions. And this is helpful for making sure that it's the coarse resolution are consistent with the high resolution grids. And we highly advise to use the GridGen tool from NSEP because that saves a lot of time and effort. The only issue with that is that it's using MATLAB. So if you're not working at a university, you don't have a discount license MATLAB, then it can be a bit expensive. But yeah, that's the way it is now. It works really nice from GridGen, and it's really plug and play, provided that the grids are put at the consistent, are added at consistent higher ranks, that the overlapping grids are put together, and if you have a system with different grids and you want to remove one grid or add another one, you may end up in having some incompatibilities, and the incompatibility is basically that Wavewash will tell you that some higher resolution grid is waiting for data from the coarse grid, but it doesn't find it because there's no matching point, or vice versa. The coarse grid is trying to put data into a fine grid that doesn't exist, or something like that. And all this is really this incompatibility can come from the mask file, the MATSTA W3 file. All right. So yeah, you can use different time steps for each grid, but to make things easier, especially if you want to optimize your system, it is recommended that grids with the same rank have the same global time step. So again, if I have an example of the Portugal, the north of Spain, and the Bay of Biscay, even if they don't have the same resolution, if you can have the same global time step, it's nice. Or at least that the time steps for different grids are integer multiples of one another. These are not required. It's just to make your life easier. And on a parallel file system, you can start by having all the grids using all the processors, just to make sure that the system works. Which means that in practice, the model will be working on one grid, and when the time step is integrated, it will work on the other grid to do the same time step, and then go again to the last grid. Once this is working, if you want to have it run faster, it's better if you have grids with the same rank that only use a fraction of the CPUs, because then they can run together, and that's actually more efficient because there's less communication between the processors. All right, and then you can take a look at these in the reg tests, at these MW3 tests up to MW3 test 05 that show different ways of running this thing. And I think this one now is in the cases folder. I'm looking at Mikael, but yeah, it's probably in the cases folder. So there's a cases folder with different cases. And so the case one is a real-world case, which is more or less what is run at NSEP operationally. So that is global system and then different grids on the coastal areas. And you can, copy and paste from that example to do your own. All right. And so the data is flowing from low resolution grid to high resolution grid. All right, so that's done. That's what was done with traditional one-way nesting. And now what the difference, of course, is that you also have the information from the high resolution is going to the low resolution. Right. So the idea is, oh, I'm getting some funny graphics. Right. At the edge of the boundary, to do the matching, the advection scheme goes back to a first-order scheme. So even if you're using a third-order scheme, at the edge it's going to be only first-order. So yeah, so you lose a bit of accuracy in the propagation in the boundary between the different grids. Of course, this has no impact if you use a first-order scheme. So you shouldn't see any difference if you do multiple grids in first order to be exactly the same results. And yeah, so imagine you have land and sea. You have some external boundary there. There's some boundary scheme to deal with transfer of energy from one to the other. And then inside of the grid, you have the internal numerical scheme, so the usual numerical scheme inside of the grid. And that's the way it works. And of course, the multi-grid, the boundary exchange doesn't use files. It's all internal using the memory. And but if you want, you can always write that to files. All right, so we can skip this. And actually, so we're still using W3 shell for our single grids, but at NCEP they completely forgot, they completely abandoned W3 shell. So even with just one grid, they always use W3 multi. It can make your life easier because, for example, the forcing, if you have, say, GFS wins for a couple of years and you're tired of preprocessing them all the time, so you can just preprocess your GFS wins on the GFS grid, and then you run a multi with the global grid and the forcing grid, and you don't have to pre-process it. Or if you change the global grid resolution, it will still always be the same forcing field file. So there's a bit of overhead. I think it's 2% increase in the cost of computation if you use multi instead of one grid. But that can be one way to run, and then you don't have to worry about the different formats of the different shell, the input file for the shell and input file for the multi. At present, there's a few features which are not supported by the multi file, and these are related to wave-mud interaction and wave-ice interactions, because we've needed to add up to 8 different forcing parameters for the ice thickness and blah, blah, blah. So this will be integrated this summer by Michael in W3 Multi, and we actually will go from a multi input file with all this funny list of bullets, but we'll have a nameless interface in W3 Multi. So that's going to change. But so right now, W3 Multi supports pretty much everything except for special mud and ice effects. Because yeah, for the mud you also need the thickness of the mud and the viscosity of the mud. And right, so the way it works in practice is that typically you have a coarse grid. So you have your grid cell here in red, and there's your grid points, and the green here will be your fine grid. And yeah, and so what is done is to make these two work together. And there's no special treatment for the obstructions. And so the way the green stuff is averaged to get the red dot value is just based on the weights and how the red grid cell overlaps the green grid cell. So for regular grids, that was fairly easy. When we moved to the capability to have Korean grids, it was a bit more complicated, and that was where the script library was introduced. If you look in the FTN folder, you'll find a script folder that contains all the tools for doing the remapping for different grids. That was on that NRL, and the remapping for the triangles and the squares also use the script library with the same idea. So that essentially one triangle will overlap several other cells, and you have to do the proper averaging to get the stuff back to the core grid. All right, so this is an example. So here it's a single grid, and you have the waves that are, this is a contour of wave height. So here you had a blob of waves here, and it was propagating through the domain. In this case, this is a case with two grids. So we have in one part the grid is the same, and then in this small region inside, you have an inner grid, and the computation is not done on this masked area. So in that grid, the waves are not computed here by the big grid, but they're computed by the small grid. And you will see that the waves go through. right? So it worked. And of course, what's happening here is completed by the other grid, the inner grid. All right, so I think there's everything it said, and that's the idea. So you have when you have overlapping grids, so you have a grid 1 goes up to here, a grid 2 goes up to there. So you need some overlap there because the waves need to be able to flow into the second grid. And there's a boundary scheme which will take care of what's happening between the two grids. And when you combine the two, there's going to be some smooth interpolation of the things. So this is what happens in 1D. And in the end, at last step, this is what you'll get as a result. All right, so this is another case with several grids. So this is one grid with third order scheme. This is another grid and a third grid. So it's the same region cut in 3 pieces, and when you put it all together, it looks smooth and nice. Then you can also play with different numerics, having first order scheme in one part and third order scheme in another part, and then you will start probably to see, no, you don't see anything. And here, yeah, see the different boxes here are the different grids, and this is the waves propagating through all that system, combined together, and you get the waves getting at the coast. And you see a bit of funny thing happening here because the third order scheme goes back to first order near the coastline, and also I think you have a bit of shoaling. I guess the black contours are the depth contours. The waves actually gets a bit more amplified by the shoaling near the coast. All right, and so here there's some, yeah, I don't know. All right, so that's pretty much what there is. So this is typically what the NCEP is running for their operational system, something like that. So they have a global grid, I think, which is half a degree, not 1 degree. Then they have some grids, for example, Gulf of Alaska. So in that case, the grid doesn't cover the full Gulf because here there's nothing happening. So the wave field is pretty smooth, so you don't need to resolve that. So what they have done is to cut out a narrow strip all along the coast and all along the Aleutian Islands and all the islands. So the grid can be in several pieces, it doesn't have to be continuous. Right? So you can have a grid with 2 different pieces together, and we have that in the Mediterranean. We have a grid in which we have one polygon around Corsica and then the French coast, and this is the same grid but it doesn't communicate. But it will communicate because there is a quarter grid, a rank 1, which is above it. So the communication happens through the other grid. And so that's another fine grid around the Aleutians. Right? So you can see the wave heights, and the green here is the islands. And when you, yeah, and that was a result from the coarse grid. So the coarse grid doesn't resolve the island. You can see there is some shadow here because there is some subgrid island blocking in the coarse grid. There's some these obstruction files that tells WaveWatch that some energy should be absorbed by the unresolved island. Okay, and when you put, yeah. Okay, so yeah, so that was with the blocking, and this one is a coarse grid but with two-way nesting, and so you can see that you get almost the same results. I mean, the blocking here is a bit stronger than it is with the two-way nesting, right? And when you plot the two on top of one another, you actually can see the dotted white line is the edge of the fine grid, and you can see that it's fairly consistent at the boundary thanks to the proper merging of the two grids. So that's the basic idea of working with multiple grids. And if there's any question. So again, as yesterday, we have going to generate the modbef file with per3 grid, but then we do it several times for each grid. The special thing here is that we do it also for the input file and for the point output. And if you have several input files, you do it several times for each input file. And then you have to tell Dorothy Multi how to use all that information. All right. I have to hang up somewhere.